तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome everybody. We continue the discussion on 2D transformations or two-dimensional transformations. In the last lecture, we have been discussing the various forms of the transformation matrix T, basically the elements, and we have almost known what are the different combination of the values of the elements create different type of transformations, and we have been mainly discussing 4 type of transformations: rotation, scaling, shear and reflection. Okay, rotation, scaling, shear, reflection, 4 different types, and we know that the combination of the diagonal elements create certain type of transformation. Off diagonal creates one, and rotation matrices are again orthogonal. We know all those properties we have seen in the previous lecture. And also I did mention that for some reason I did not discuss the very simple fundamental transformation as the translation. Translation was not discussed, and it is the reason why we will know soon. We will just look into the slide to see an example of translation. As you see here, translation is a movement of one object to another, and this slide there is an object located. Yes, it is again the house, light blue structure, basically something like a square and a pyramid sitting on top, which has been given a translation of 5 units along x axis and 1 unit along y axis. The coordinates of just 1 pixel value on the left bottommost corner of the structure is given, which is 2, 2 on the left side here, and you add 5 to 2 you get 7, you add 1 to 2 you get 3. So 2, 2 is displaced to 7, 3, and all other coordinates are also displaced in a similar manner. Okay, because we are talking of rigid body transformation, so all of these points or the entire object undergoes the same type of transformation like the translation. If you want to replace this by matrix equations, the translations, you will see you can easily represent by an equation like this. You remember the coordinates of A and B are 2 cross 1, basically it is a vertical vector, column vector, and there are just 2 elements, and so you add Tx to x and Ty to y, and you get the coordinates of the displaced point or for the entire object. So that is the okay. And translations basically do happen in almost all sorts of transformations. Okay, it is then inherently, if you do not write even an expression and do not give it a translation, also it is there in other type of transformations, as for example rotation. Rotations of any objects which are not centered at the origin undergo a translation. Is the same for scaling. When objects and lines are not centered at the origin, anything which is not at the origin and undergoes rotation and scaling, those objects including lines and points also undergo a translation in some form. We have seen examples of rotation earlier, we will see again today, and it will be clear to you that translation inherently happens with most other types of transformations as well. But of course, if the object is at the point is at the origin or the line intersects the origin, there may not be in translation. When you give it a rotation or a scaling, there may not exist any such things. Or we will say that the origin by itself is invariant to scaling, reflection and shear, but it is not invariant to translation. That is indeed a very nice observation, because if you plug on the top of the expression given on the top of the slide here and substitute A is equal to 0, which is the origin or the coordinates of the origin in 2D space, you get B equals TD, which is Tx and Ty. So the origin is shifted based on the coordinates or the amount of displacement vector basically the translational components might shift the origin. You should be able to shift something to the origin and also the origin to somewhere else, but of course you cannot scale an origin, you cannot reflect it, you cannot share it, that is the key. So, you see the expression which we talked about in the last class in terms of the transformations, we use multiplication, matrix multiplication in general to represent all transformations in 2D. In except translation we have a addition instead of a multiplication. So, we have a mathematical problem. We cannot directly represent translations as matrix multiplication as we can do for, say, these are examples in figures of scaling and rotation. Again, it is the same structure like a house which is scaled from scaled up or scaled down, that means expanded or contracted, or something you can make the house rotate about its origin. And in this case there may be inherently a translation, but when you represent these transformations you would use a matrix multiplication operation, okay, mathematical model, but for translation I have given in the previous slide we are forced to use an addition. How can we combine these two, because it is not easy to do that. So, how can we represent translations in our general transformation matrix which is ABCD, 4 parameters, where do we plug in the transformation elements for the translation, and it's made possible with the help of what are called the homogeneous coordinates. We will see what are the homogeneous coordinates or the representation of a point in homogeneous coordinate system. We first see the 3 cross 3 matrix or the matrix transformation matrix in homogeneous representation, but the homogeneous coordinates are there now to the right of you. Instead of x y we have a third element called w. In some books you use h instead of w, so you can use it interchangeably, but stick to one again, h or w, and x y w are the original coordinates of a point before transformation is transformed by a 3 cross 3 transformation matrix, and you get x prime, y prime and w prime. Okay. What is the significance of w and what is the role? Before going that, if you just take out the 2 scalar linear equations out of this matrix equations, you get x prime is ax plus cy plus tx, and of course y prime is similarly bx plus cy plus ty. And now what is this homogeneous coordinates? Each point is basically now represented by a triplet x, y, w. So, there is a third element which comes. Remember, it is not a 3D space, we are still talking of 2D space. X, y are the coordinates value. What is the role of w? That is the homogeneous term, which is just a parameter, and we will say once given x, y, w, you divide the first two x comma y by the third element w or the third parameter w, and you get back your Cartesian 2D coordinates. That is what the last line says, x by w, y by w. How do you get this? Take the first two, divide by third, okay, and those are called the Cartesian coordinates of the homogeneous point. So, homogeneous points coordinates are this x, y, w or x, y, w here, or in the equation on the right hand side, x, y, w or x prime, y prime, w prime. But to get the Cartesian coordinates, take the first two, divide by third, you get x by w, y by w, you get the actual coordinates which you have been talking for. W could be equal to 1. There is, now this is a interpretation of homogeneous coordinate representation. Any point in this vector line which comes out of this x, y, w space, you can visualize this to be now a 3D space where w could be z, but actually it is not z, because x, y are the coordinates, and any vector which points in this direction x, y, w, ph is a point in this homogeneous space in x, y, w space, and it also points as a vector along a certain direction, and any point on this line or this vector in this direction basically represents a single point in Cartesian coordinate system, which is this one. So, the P2D is nothing but x by w, y by w and 1, that is obtained by dividing all the x, y, w triplets by the third element w, and that is what gives you the first two of those give you the 2D coordinates. So, basically the intersection of this vector with w equal to one plane, that is you draw a plane which is parallel to x, y axis and normal or orthogonal to the w axis. The w axis is the perpendicular or the normal to this plane, and it intersects the w axis at w equal to 1, which is marked here at the center. So, this plane, which is again I repeat parallel to xy plane, perpendicular to w axis, intersects the w axis equal to 1. This plane intersects the corresponding vector, this ph vector, at a point which will give you the 2D coordinates of the actual point in 2D space. So, this is the interpretation of homogeneous coordinates. Okay. More examples on this. If you take any two homogeneous coordinates x1, y1, w1 and x2, y2, w2, they may actually represent the same point if and only if they are multiples of one another. A typical example is 1, 2, 3 and 3, 6, 9. If you see here, I did say that you can obtain the 2D coordinates from the homogeneous one by dividing the first two elements by the third. So, 1 by 2, 1 by 3 and 2 by 3 are the respective Cartesian coordinates. You can get the same thing here, because 3 by 9 is 1 by 3 and 6 by 9 is also 2 by 3, or you can multiply all the values by a constant scalar quantity 3 and you get the other one. So, you can scale down or scale up, it is basically the same point. There is no unique homogeneous representation of a point. I can say this is 1, 2, 3 is one point which is equivalent to a 1 by 3, 2 by 3 in Cartesian coordinate system. It is same as 3, 6, 9, or I can take it to be 6, 12, 18, or I can take it to be 100, 200, 300. Multiply this 1, 2, 3 by any all the elements by a same quantity k, all those represent basically the same point. This is, you can start to visualize the figure which I showed you in the previous slide, the intersection of that vector with that plane. Any point in that line or that vector can be represented by values, intersection gives a unique point. All triplets of the form t dot x, t dot y and t dot w form a line in the x, y, w space. We talked about this vector earlier on, and you get that by dividing, of course, by w. T dot w, if you divide, you get x by w, y by w from this triplet. And the Cartesian coordinates are just the plane w equal to 1 in this space. We have seen in the previous slide, I am talking this again. That is how you get the Cartesian coordinates from the homogeneous coordinates, by intersecting this vector with the w equal to 1 plane, or dividing the first two by the third element. Well, what about w equal to 0? W should be a non-zero quantity, because when you are talking about w equal to 0, you are talking about points at infinity in 2D space. So, we do not talk about those in real numbers world numbers which can be represented and stored in a computer. Infinity cannot be stored, so you do not need to bother about that. But just the physical interpretation, w equal to 0 represents points at infinity. So, once we know what are the homogeneous coordinates and its representation, we can now relook at the general purpose 2D transformation matrix in general, which should be able to handle all different 5 transformations, 5 type of transformations, and this is a general purpose transformation matrix. Okay. So, there are 9 elements, 3 cross 3 matrix. We need a 3 cross 3 because homogeneous Cartesian coordinate representation talks about a 3 cross 1 element column vector. So, you need a 3 cross 3 element transformation matrix. Okay. The submatrix consisting of the top left 4 elements A, B, C, D, these are the parameters involved in scaling, rotation, reflection and shear, as was the previous case, though that part is unaltered. We still have that A, B, C, D with the same significance as we have been talking in the previous lecture, with the 4 different type of transformations of scaling, rotation, reflection and shear. So, there is absolutely no problem with the A, B, C, D, thus corresponding 4 parameters behave in the same way. We still have 5 different parameters, out of those which 2 represent translation is most important to us, correct. We need to know what is translation. Well, I talked about now 2 different notations, a pre-multiplication and post-multiplication operator to obtain the new coordinates b from A, and if you are pre-multiplying the coordinates A by t, the translation parameters are p, q, as given here at the bottom. Okay. So, the third column first 2 indicate translation if you are pre-multiplying. If you are post-multiplying A by t, you have mn, the first 2 elements of the last row of the matrix T indicate transformation. We talked about these pre and post scenarios. Row A becomes either a row or a column vector depending upon whether you are pre-multiplying or post-multiplying, and depending on that, the corresponding translation parameters Tx and Ty could change place, do change place in fact. They could be either Pq or Mn depending upon whether you are using B equals T multiplied by A or A multiplied by T. Okay. So, that is okay. Of course, you will have another question, that if Mn is the translation parameter, what happens to Pq, and if Pq is the translation, what happens to Mn? We will hold on to that for the time being, do not worry about it right now, but we still have a 9th parameter which is the S. Can you almost guess what S could be doing? Well, I leave it as an exercise for you to try out and write equations by keeping S as non-zero and A and D to be 1 and all other elements. That means, basically take this as an identity matrix with S equal to 2, and all other elements C, M and N, P, Q, B, these are all off diagonal elements to be 0, A and D diagonal elements to be 1, and S to be 2 or 3. You see, I am sure if you do not make a mistake, you will find that the S gets involved also in uniform scaling. Very interesting. Coming back to composite transformations, because now we know to handle all 5 different transformations. That means reflection, rotation, scale, shear and translation. Of course, we did not discuss necessarily in this order, but there are 5 different transformations which are possible for by manipulating the different elements of the transformation matrix. And what happens now when we want to apply 2 different transformations either together or one after the other? That is known as composite transformations, which states that if we want to apply a series of transformations T1, then T2 and then T3, not in some sense together, but in a sequence. The sequence is very important. We will come to that in a moment from now, but you have these 3 transformations applying, let us say, one after the another. Effect is the same as if it is applied together maybe, and it is applied to a set of points or a single point. We can do it in 2 ways. Number 1, we can calculate from the vector P, which is the coordinates of the point P. Of course, we are all discussing homogeneous coordinate representation, and the T is also a 3 cross 3 transformation matrix which could represent any transformation. We are in this case we are taking pre-multiplication of P by T. So, we multiply P by T1, you get P prime, then from P prime you can pre-multiply it by T2 to get P double prime, which means that you are first applying the transformation of T1 on P to get P prime, then you apply transformation T2 on P prime to get P double prime, and ultimately on P double prime you apply a transformation T3, you should be able to get P triple prime, or basically the resultant coordinates of the point P after 3 successive transformations. You can do 3 different such multiplications one after the another, or you can do the other way. You can calculate T as a product of all the 3 transformations and then apply and then obtain P prime as T multiplied by P, where T is given by this. This you can easily derive from the number 1 step. You start substituting P double prime here and then P prime there, you will find that the T is nothing but a sequence of matrix multiplication of T1, T2, T3, and then you get P prime by a single matrix multiplication. Actually, in most scenarios you have this multiplication matrix form known, and if it is known, actually you do not have to compute for a given problem the resultant matrix T for 3 transforms. So, in fact, you are saving a lot of time in this process, and method 2 is optimal. That means, it saves a large number of additions and multiplications, and it gives you low computational cost or low computational time. The complexity, the computational complexity of the second step operation becomes really low. Computation complexity is really low, as it needs approximately 1/3 of as many operations as in step number 1. Therefore, we concatenate or compose the matrices, that is, get this T1, T2, T3, all of them together, put it to one final transformation matrix T, and then apply to that to all the points or to a single point to get the final transformed point. Okay. Just to take few simple examples, as I was talking, if you want to apply 2 translations one after the another, that means you need to translate the points by Tx1 comma Ty1, x and y indicate the translational components along x and y direction respectively, and then you want to translate it by again by Tx2 Ty2. I leave it as an exercise for you to find out that the overall translational matrix, which is a multiplication of the 2 translational components, we are taking pre-multiplication in this case, is given on the right hand side. Okay. So, that is very simple, and I leave it as an exercise for you to find out that the scaling effect is also similar to that of translations, and these scaling coefficients will come along the diagonal elements of the matrix T. Rotation is a little bit tricky, but there are good methods to solve it. You need to rotate, the problem says that you need to rotate by an amount or an angle theta 1, and then you need to rotate it by an angle theta 2. What, instead of applying 2 different transformations, one for theta 1 then for theta 2 in succession, you put in the transformation matrix for rotation an angle theta 1 plus theta 2 itself in place of theta. In the original transformation matrix, where you remember you had a cos theta minus sin theta cos theta, you instead replace that theta by theta 1 plus theta 2, and then you better do that instead of doing the second stage, which will be cos t. That means calculate T1 for theta 1, T1 to T2, and then multiply them. If you multiply them, the effect which you get basically is the same by replacing theta by theta 1 plus theta 2. Take it as an exercise that both step 1 and step 2 gives the same result of the rotational matrix. Okay, we will come into that form. Often you need to rotate about an arbitrary point in space, because if you think of the rotation matrix which we discussed in the previous lecture of transformation, it was basically rotation with respect to the origin. That means you are rotating with respect to the origin. So, we have the transformation matrix which helps you to rotate about the origin. What about trying to rotate about any arbitrary point of space? What do you mean by that? Okay, let us take the revolution or rotation of the earth. Earth spins about its own axis. So, the transformation matrix which you know for rotation, you can apply if you are applying the rotation about the center point about the earth, that is fine. But let us say the case when let us take the case of the moon. Okay. So, the moon, there are points which are rotating on the moon about the center of the moon. So, you are not the points actually, of course, the moon revolves around the earth like the earth also moves around the sun, but if you are taking, if you are trying to move an object at a point with respect to some other point which is not the origin, we do not have the transformation matrix, we will derive it right now. What is the first step? Okay. As we mentioned above, rotations are about the origin. Okay. Look into the slide, you will find out. Okay. As written that as we mentioned before, rotations are applied about the origin. So, to rotate about any arbitrary point P in space, there are two steps. Translate so that the P coincides with the origin. Okay. As you see in the slide here, a new paragraph, yes. So, to rotate about any arbitrary point P in space, translate so that the P coincides with the origin, that is the first step. Second step, rotate. Now, rotate, we can rotate now because the point has become the origin or the origin has become the point, whatever way you look at it, and then you can translate it back. So, the steps to implement the overall transformation are: translate by minus px comma py, which are nothing but the x coordinates of the point P and y coordinates of the point P. So, you are basically translating the point P to the origin, or the origin moves to the point P, whatever way you look at it. Then you rotate using the original rotation matrix, and then finally translate it back. Let us have an illustration of the steps of the process first, and then what we will do is look at the overall matrix of the transformation. Okay. So, rotation about an arbitrary point in space, we are discussing this point. I take the sample of the house without the shading, and I want to rotate this house with respect to the point P1 which is at the bottom left of the screen, not with respect to the origin. If I want with respect to the origin which is here, there is no problem, because I have the rotation matrix for that, and the whole object along with point P1 should rotate. Basically, when I rotate with respect to P1, the point P1 will stay, everything else will rotate around that. So, that is the difference between rotating about a point, arbitrary point in space. In this case, arbitrary point is on the object, or with respect to the origin. If I rotate about the origin, I repeat, the entire object will rotate along with all the points, but in this case with respect to point P1, the point P1 we will see it is there, the other positions of the other points will be changed. So, what was the first step? If you recollect, translate it to the origin. Translate P1 to the origin by translation vector minus Px minus Py, we have seen that. Now, we can rotate it because P1 is at the origin. So, after rotation by an amount theta, you will find that the, now I have drawn a red line as the x axis just to show that it is equivalent to transforming the two dimensional plane itself, but basically you are rotating only the house, not the other axis. Okay. And finally, translate it back to P1. You will compare the first figure on the top left and the final figure form on the top right. You can see that the point P1 has not changed its position. The structure has basically rotated by an amount theta. So, this is an example of a sequence of the stages, different stages or steps involved in rotation about a arbitrary point P in space. If you wanted to rotate the structure about this origin, actually what happened would have happened with respect to theta, the structure would have gone and almost gone past the y axis, vertical axis, or would have at least gone near to that. So, you can, I leave that as an exercise for you to rotate the structure about this origin, that you will require a simple rotational matrix to do that. So, let us come back to the equations. We had seen that there are 3 stages. So, we have a translational matrix, then a rotational matrix T2, and then a translational matrix T3. All these are general transformation matrices 3 by 3 representing homogeneous Cartesian coordinates form, and the corresponding matrices are given here. Okay. So, the T1 with minus Px Py is given on the left hand side, multiplied with this is the original rotational matrix with respect to a point at origin, and cos theta minus sin theta and so on, and all are 3 by 3 matrix, finally translating the point back. So, if you multiply all these 3 matrices, I leave it an exercise for you to find out. You can actually multiply by starting with the last 2 or the first 2, does not matter. You should always, if you are correct, you will get back this final expression. So, what you need to, almost the system or a programmer needs to remember these expressions of the elements of this for a general purpose rotation. Px Py are the coordinates of the point about you which want to rotate, and theta is the amount of rotation. So, that is the final form of the rotation of an object or a point about any arbitrary point P in space. Okay. So, that is an example of a composite transformation, that means several transformations together. Okay. Well, you can also talk about scaling about an arbitrary point in space similarly. Okay. And since we have transformation matrices which can scale with respect to the origin, the similar concept as we did for rotation is applicable here. That means you translate P to the origin, scale, translate it back. Okay. So, you look here, these are the 3 stages: translate P to origin, scale, translate P back, and 3 transformation matrices. Sx, xy are the diagonal elements. For x non-uniform scaling could be Sx not equal to Sy, but these are diagonal terms, and we have also the translational parameters at the T1 and T3. Okay. And I leave it as an exercise for you to check out that the overall transformation matrix T after multiplications of these transformation matrices will give you a expression which is given in the figure below. I would like you to note down this figure, but also verify whether you are getting this particular expression. If you are not getting, you are making a mistake, please check your expressions whether you have taken the correct form of T1, T2, T3 and multiplied one after another correctly to get this final expression of a T, which is what? A scaling about an arbitrary point in space, and that is also a composite example of a composite transformation. Okay. We talk about reflection through an arbitrary line. Why arbitrary line? Well, we have reflection matrices which were reflecting about certain specific axis, like you can reflect about x axis, about the y axis, or a complete diagonal line which is equation of the line mean y equal to x or y equal to minus x. As you can think of, now if I have an arbitrary line, say y equal to mx plus c, and I would like to reflect it about that, and I hope you remember reflection. We are talking about reflection with respect to a plane or a line, and you could visualize with a mirror about what you mean by reflection in 2D space as well. Okay. Now, this composite transformation you need 5 different stages. Why? Of course, we were talking about before rotation and scaling to translate to the origin and back, that must be there, number 1. In addition to that, you may need to rotate that line or the coordinate such that the arbitrary line coincides with the x axis or the y axis or y equal to x axis. You need all that because, as like the previous case of rotation and scaling, you had the original transformation matrices with respect to the origin. In this case, for reflection, you have the form of the reflection matrix helps you to reflect an object about certain specific lines, y equals x, y equals 0, x equal to 0, that means horizontal, vertical axis or whatever it is. So, you must make the arbitrary line coincide with some of these special lines, and then only you can apply your reflection matrix. Then of course, you rotate, translate back as you have done before in the case of rotation and scaling to get back the composite transformation matrix. So, look back into the board, there are 5 different stages. Translate the line to the origin if the line is not passing to the origin. If it is passing to the origin, the first and the last step may not be necessary. Okay. Otherwise, generally translate the line to the origin, rotate the line about the origin, reflect, use the reflection matrix to reflect the object or the point, reverse the rotation, then reverse the translation process back as well. Well, 5 different stages. So, I will talk of a G general reflection matrix, a general reflection matrix, composite matrix, transformation matrix for generalized reflection. I will talk of a composite matrix of a generalized reflection, we talk of translation, then a rotation, then a reflection, then a reverse of rotation, which you know, because since rotation matrix is orthogonal, so this R inverse is nothing but this transpose, and of course, you also take the inverse of the translation matrix at the end to, I leave it as an exercise to compute the overall composite matrix in that case. Now, we discuss about commutativity of transformation. That means, if we scale, then translate to origin, then translate back some sequence of transformations, let us say arbitrarily chosen, is that equivalent to translate to origin? That means, can this process be interchanged in the sense that can the sequence be disturbed and can we have the same result? If we scale, translate to origin and then translate back, is that equivalent to translate to origin, scale and translate back? Is the order important? That is the question. Is the order of transformation which is dictated by the order of matrix multiplication or vice versa? The matrix multiplication dictates the order of transformations, or the order is dictated by the sequence of matrix multiplication. Is the order important or unimportant? What do you think? Well, I am talking about scenarios that when does T1 multiplied by T2 equals T2 multiplied by T1. If you go back to matrix theory, matrix multiplication, the order is important. You cannot change the order and get the same result. That means, in general, you will not have, if you have arbitrary matrices and multiply T1 and then with respect to T2, T1 post multiplied by T2 is not equivalent to T1 pre multiplied by T2. So, that is what given in this. Is it same? It is generally not, but in certain specific cases you may have T1 multiplied by T2 equals T2 multiplied by T1. That means, pre or post multiplication of matrices does not make a difference, but in certain special cases, in general not. So, it is mathematics of matrix multiplication which is dictating the order, dictating that the order of the multiplication as well as the order of transformation is very, very important. You cannot jumble up the order and simply say that I am expecting the same result and I should get the same result. In general, you will not get it, but in some cases, yes. The cases where T1 and T2 being post multiplied or pre multiplied gives you the same, we will see in the slide now. In this particular table, the cases where T1 multiplied by T2 is equal to T2 multiplied by T1. That means, you can take in any order, pre or post multiplied. If you take two translations, you take two successive scaling operations, two successive rotation operations, or a special case of a uniform scale followed by rotation. If these are the pairs of combinations of T1, T2, you check for yourself that the order is unimportant. You can apply it in any order. You can apply the translation T2 and then apply translation T1, or scale T2 then scale T1 is the same as scale T1 and then scale T2. Okay, I am talking of any. You should take a pair of transformations in any horizontal row, not along the column. Okay, that means you can take T1 as rotation, then T2 as rotation. Reverse it, you get the same result. Okay, I am not asking you to combine translation and scale. Take two translations, take two scale, reverse the order, you get the same result. That means, in these specific cases of 4 cases as given here, these are 4 examples only where the order is important. Otherwise, in general, the order is very, very important. You cannot swap or jumble up the order and reverse it and expect the same result. Just to highlight the importance of this order, I have taken an example. This example shows the order in which I am scaling and then translating. That means, you look at the colors, the original object is marked as red, it is the same house object, and then I give it a scaling which gives you a greenish house, and then I give it a translation which gives a blue house. So, the red house gets scaled first to the green and then translated to the blue house. And if I reverse the order, what I am doing, I first translate from red I get the blue, from the red I get the green, and then I scale it down, I get the blue house. As you can see, the final result is different. Remember, the order is red, green and blue. So, you start from red, end in blue, reverse the order, as you can see that the final result is different. The final result is marked in blue. This is the final result of scale and then translate. This is the final result when you translate and scale. We will take another example. Rotate and differential scale. that means you are first rotating the house marked in red to a greenish position, the position marked by the green house, and then give it a differential scale. We are talking of non-uniform scaling, that is meant by differential scale, the other term which is used, and that is the final position given by the house marked in blue. But if you alter it, that means given a differential scale first and then rotation, you can see now that the red house given a differential scale or a non-uniform scale gives rise to the green house first, the house marked in green is what I mean, and then you give it a small equivalent amount of rotation, you will end up with the blue. Again you see that the final result is different. These two examples show that the order in general is very, very important. You cannot just jumble up the pre or post multiplication operators and expect the same result. And talk of coordinate systems, many type of coordinate systems in 2D exist. One is called the screen coordinate system. This is the coordinate system used to address the screen or what are called the device coordinate. The pixels actually reside on the screen, that is referred to as screen coordinates. We also have world coordinates, which are the user or the programmer defines, a user defined application specific coordinate system having its own units of measure, axis, origin, etc. Those units may not be in pixel units, it could be in inches, millimeters, kilometers, whatever it could be, feet, some length units sort of is necessary, and the user and the programmer knows. And you have a windowed based coordinate system. It is a rectangular region of the world or the screen that is visible, and it has its own units, basically again in pixels in most cases. And of course, you have a viewport on the window, which is a rectangular region of the screen space that is used to display the window. So you have a window of the world, I should say, and a viewport on the screen. To understand the different coordinate systems and their relations, you look into the screen in terms of the world on the system and the windowed coordinate system on the left hand side, and the screen coordinate system and the viewport coordinate system on the right hand side. Well, you see that the window is a small part of the world coordinate system, and a viewport is a small part of the screen coordinate system. And if you are displaying a small circular patch or a circle, the window takes a part of that arc of the circle, and you can display that in any of the viewports. There are two viewports displaying the window of the world, and you can see the corresponding arcs of the circle in two different viewports. You can define that viewport anywhere on the screen. Okay. Now, but you need a transformation matrix. So, we are still in 2D transformations. You need a transformation matrix to transform from at least the window to the viewport. Of course, window is described with respect to the world, and also the viewport is described with respect to the screen. So, if this is the world for you, now you could have a small window where you can see only my face, maybe see, or you can some characters written on the screen, some part of it, or you can assume this to be also your screen, and you would like to have a small viewport and nothing else outside the viewport. You want to make it visible. It's just something like looking through a window in your house, and you see a small part of the world through the window. That is the example of a window or a viewport, the port through which you are able to see. That is what is being talked about. And you need a transformation to transform from window to viewport. So, the purpose is to find the transformation matrix that maps the window in world coordinates to the viewport in screen coordinate system. And we talk about a windowed XY space system denoted by x min, y min, x max, y max, the corresponding minimum and maximum coordinates in x and y direction respectively. And similarly, also you have a viewport. Instead of xy, you use typically another coordinates uv. Sometimes xy and uv are used interchangeably within the device coordinates or window or viewport. We will have to get used to this uv. And similarly, in the uv space, you have a minimum or a maximum coordinates defined as u min, u max, or v min, v max respectively. Okay. So, the overall transformation is translate the window to the origin, and you have to scale it to the size of the viewport and then translate it to the viewport location. So, these are the three transformations involved in the overall transformation matrix, where you want the window to be transformed to the viewport, because you want to display a section of the world in a particular section of the screen, which is the viewport. You want to don't display, you don't in general want the entire world. World means the entire all set of pictures which you are drawing on the screen, or which you have modeled basically. You don't want to draw all those pictures on the screen. You want a certain section of your world which you have defined yourself. The world in this case talks of the pictures and the objects which you want to draw, or your model basically in mathematical using mathematical tools or mathematical functions, and you want a part of that to be displayed not maybe on the entire screen, part of the screen. So, that part of the screen is the viewport, the part of that world which you want to display is the window, you want to take this window and put it in the viewport. So, that is the transformation we are talking about, and let us look at this transformation matrix as given in the slide. Now, we are talking of the overall transformation matrix MWV, that is the notation which I have used. If you look back into the slide, it consists of 3 transformations, a translation, scale and translation again. We are now already used to this type of transformations. So, T with U min V min multiplying by a scaling matrix and then a transformation matrix again, and this where the scale factors for the scaling matrix is given by the ratio of the maximum minimum coordinates along x and u respectively and along v and y respectively, and if you plug this Sx and xy into the scale matrix and then multiply T, S and T, the final form is given at the bottom of your screen. M is the overall matrix for transformation, WV subscript indicates world to viewport, sorry, window to viewport. So, we are talking about a overall transformation matrix to transform from window to viewport. M window to viewport is given by this. Sx, Sy are the corresponding scale factors for the scaling matrix. X min, Y min, U min, V min are also known, and U max, V max is also taken care of by the Sx, Xy. So, this is an example of a transformation in the device world to device coordinates. Yeah. So, after we had seen this nature of the transformation matrix, which could be used to provide the transformation from the world coordinate systems or the programmer's coordinate system or the user's coordinate system to a viewport within the device or screen coordinates. We will take an illustration now of an object which will do this task. Okay. We will take an example, illustrative example of what do you mean by this transformation, okay, as we go along. So, window to viewport transformation, we had seen the matrix representation, it is a combination of a translation, a scale and a translation back again, and we take an object here. A simple square shaped object is taken as you see in the slide here. It is a small square shaped object which represents the window in world coordinates. It typically means, that means a programmer or a user may have all his pictures and objects drawn all over in this world over all x and y values. It could be positive or negative, but at the end what he would have wanted is, or he would have liked, or he desires now at any given point of time, let us say he wants his objects drawn from x min, y min to x max, y max, all these points to be, all the objects to be drawn here to be put in a particular position in the viewport, somewhere in the viewport it must be put, and the viewport belongs to a small part of the screen. Okay. And so, the first action is to translate it to the origin, and that is, so x min, y min becomes 0 0 and x max, y max, which is the top right corner of the box or the window, will become now what, x max minus x min, y max minus y min, that is the top left corner coordinates after translation. You want to scale it back because the size of the viewport may not actually match with the size or shape of the window. Size is more important rather than the shape. We typically take rectangular shapes. So, size is a important factor. So, we scale. So, scaling matrix will come into play and it will implement the scaling. It will scale the translated window to the origin to another shape or size at the origin itself, and then we need to translate it back to the point where the viewport is in the screen coordinates. So, you are already into u and v after the scaling, and we now translate in the uv space to a point u min v min given by the left bottommost coordinate of the viewport, that is the viewport bottommost coordinate in the uv space where we wanted the viewport to be. Okay. So, that this is an example of the window to viewport transformation as it happens using the transformation matrix, the composite transformation matrix. So, we have seen lots of examples of composite transformation matrices. Now, we will take a small exercise about transformations of at least one case of more than one line. Say, let us say we will take transformation of parallel lines. I will probably encourage you to take transformations of intersecting lines also, but let us say you have two parallel lines, of course anywhere it is parallel. Let us say there are two parallel lines and I want to give it a transformation. That means I want to rotate both of these lines simultaneously, I want to translate them, I want to maybe scale them, do some transformations. We are talking of a general transformation matrix. So, let us consider two parallel lines as given in this screen. One runs from A to B with coordinates x1 y1 to x2 y2 as given in this screen here, and the second line runs from coordinates C to D x3 y3 to a point x4 y4, and let us see, that means there are two lines A B and C D, okay, and I want to transform these lines by a general transformation matrix A B C D. Now, of course, I have not taken homogeneous coordinates here, does not matter, you can work with the general transformation matrices in 2D without the translation. Let us say a translation also we know what to do. There is actually no problem with translation when you are translating parallel lines, they will remain parallel anyway. But what about other? If we scale, if we rotate, okay, if we reflect, if we give it a shear transformation, parallel lines, if we do any sort of transformation, what happens? Well, I leave it, I will not solve this problem entirely for you, but he gave you hints and direct you to solve it. The slope of the lines can be computed by this expression, m is the slope of the line. Given two endpoints of a line, you can always compute the slope. I hope you know this from fundamental mathematics or geometry. Is given by y2 minus y1 divided by x2 minus x1 or y4 minus y3 x4 minus 3. So, both are same, that is the slope of both the lines AB or CD. Okay. You solve the problem by transforming these lines by a transformation matrix T given by A, B, C, D. So, how you solve it? What I would request you to do is you transform A by T, B by T, C by T also, and also D. All the four coordinates, that means the two pair of endpoints or the corresponding pair for each line, transform it by T and then compute the new slope. Compute the new slopes, as you say, that is m prime from the transformed endpoints, and try to compute the slope of the transformed lines m prime as a function of these elements A, B, C, D and m, that is the original slope of the line, and you will find that the slope of the transformed lines, both the lines get an equivalent transformation, their slope also changes in the same way. That means from m you reach another m prime given by this expression. This is the exercise which I am leaving it to you at the end of this talk almost, that the m prime can be written as an expression given by b plus dm a plus cm respectively. As you see, if you look back into this expression here, the functional form for m prime depends on the original value of m, that is the slope of the parallel lines before transformation, and the elements of the transformation matrix. It does not depend on what? It does not depend upon the coordinates. That means you can take any points A and B on the line, any point C on those parallel lines. The transform lines which had the two parallel lines which had a slope m, after transformation will also have the same slope m prime. That means parallel lines after rigid body transformation will remain parallel, they will not change. Rigid body transformation has this property. You take two parallel lines of an object or any object shape, it could be a house or any other structure, give it a rotation, give it a shear, give it a reflection, give it any or even translation for that matter, and the two parallel lines remain parallel. Yes, the slope of that line changes, that is given by the expression here, which you must work out. Solve it yourself and see. If you cannot solve it, you can contact me by email or send it by post for me to correct it, or you can contact your teachers. But what the lesson we learn is, parallel lines transformed remains parallel, but their slope changes. That means they had a slope m and it has now become m prime, which is a different slope, but they again remain parallel. That is interesting. I will also ask you to take another exercise to find out if you have two intersecting lines and their intersection point is computed. After transformation, you get a new point of intersection, and the entire object which is transformed by an equivalent transformation matrix, the corresponding intersection point is also transformed by the same T. This is derived from the law or the concept that all points of a rigid object are transformed equivalently by the same transformation matrix, which is the transformation matrix for the entire object or for all points or for all lines or for all parts of the object. As long as the body D is rigid, does not change its shape or size. We did talk about deformable structures, which we are not discussing here. We are talking of rigid structures which we see in front of us, not like the cloth on the paper which can be deformed. We are talking of rigid objects, and when they are transformed, rigidity is maintained, internal structure details are maintained, and but the transformation takes the points or the object to some other point, all right, but their internal structure details are adjacency and their distances between any 2 points, the slope corresponding slope relations of 2 lines, any parts of the object remain the same. So, that is the lesson which we learned from rigid object transformation. We will wind up with simple examples of transformation once again, just to enlighten you. If you have done with a lot of mathematics, you must trust me, you have to believe me that this is the beginning of mathematics of this course. As we go along with more and more algorithms, we will have more and more of this mathematics, more to do with linear algebra, in some cases algorithms, differential and mostly vector calculus and vector geometry and concepts like that as we move along. And we will go ahead with some simple nice illustrations, very simple, all right, but now in the sense that the examples illustrate the effect of transformation, which is fundamental to animation. When you are talking about animation, which we will discuss at the end of this course, animation involves motion or some sort of movement, and movement along a path. So, you must define the path, define the pattern of movement, and it is that you need the transformation matrices to in fact move any parts of the object or the object by itself. So, we will see how transformations are used to create animation with the help of simple structures. Okay. Let us take an illustration here. I take the same house structure and I wanted to rotate it about the origin. It will create an animation type of motion, but you have to assume here that I am doing it incrementally. The amount of rotation I am doing in by small thetas, step by step, and it will, if I do it very fast, this is the effect which I will get. So, it rotates by not a smooth motion, all right. I was trying to create an effect of an animation. I go back and give you the motion again, the example of rotation. Okay, or a sequence of small rotation steps giving it a rotation. So, if in effect it has rotated and it has created animation. You will see another effect here, where the object is scaled and rotated simultaneously, rotated about its centroid or about some point within the object, and it is also scaled. It was a small object and it is enlarging out. Okay. I will repeat the process again. Simultaneously, it is enlarged, zoomed out, and as well as rotated. Okay. These are 2 objects, one coming through a spiral path, another coming through a scale and a zooming scale or zooming effect along with rotation, which we have seen earlier. I play it again, 2 objects simultaneously joining, but following 2 different paths of transformations. Okay. And the very last one is a simple case of rotation. I think I showed this structure earlier. You see a structure of a house which rotates about the origin, and then of course also after rotating about 90 degrees, it also changes its position at that end. Okay, that means it rotates about itself. I will repeat that process once again. Rotation by origin, rotate about itself, rotate about origin 90 degrees, rotate itself, rotate about origin, rotate itself, rotate about origin by 90 degrees. So, these are the sequence of examples of transformations. Rotations we have seen, scaling and or a combination of rotation, scaling, and then of course, if you have multiple objects, as like in the previous example, multiple object paths can be created and you can have multiple objects animation. Okay. So, we stop the lecture on 2-dimensional transformations right now here, and the next lecture will start with 3-dimensional transformations, and where we discuss objects which will be transformed in 3D. And interestingly, we will find out along with transformations in 3D, which involves all the transformations like translation, rotation, scale, shear, reflection, you have a special case of transformation in 3D which does not exist in 2D. You can almost guess it now. It is what we call as projective transformations. Perspective, orthographic, isometric, various types of projective transformation exist only in 3D. There is no scope of that or no application of that in 2-dimensional transformations. 2-dimensional transformations, we have 5 different categories: translation, rotation, scale, shear, reflection, and in 3D we have all these 5 plus projective transformations. We will see when we go to the next lecture. Please solve these examples of 2D transformation problems which are given inherent within the lectures itself. Thank you very much.